Hi everybody, welcome back to the channel. So in today's video, I'm going to talk about a common challenge in blockchain development, in blockchain programming, especially for the EVM ecosystem, when you write a smart contract in Solidity. So this challenge is more basically unique for larger scale commercial industrial projects. So it's not necessarily applicable for small tokens, NFT project or things like that. This is rather for more sophisticated banking systems, or DeFi projects with, a lot of sophisticated smart contracts, multiple layers, permission management, DAO, and different contracts, when we have this sophisticated system, like a sophisticated software, right? So this challenge is something that actually I frequently face with, especially during, when I deal with commercial projects, when I analyze them or develop the code or perform security audit and this kind of work. And I guess that's a common issue also for many smart contract engineers, especially for Solidity engineers. But it could be the same actually for other ecosystems as well, because it's the same principle. The issue here is not more about gas optimization, gas golfing, and those kind of things. It's more about the file size, about the smart contract size, more specifically. So sometimes you have like factory smart contracts. You have some common, basically smart contracts that basically are that contains various operations. They are like a hub. They are like a central, point in your project, or they are more central. So in this situation, we might have multiple instances, many import libraries, and many basically code inside of the code that make it really large. So what large means in the context of EVM smart contracts, So large here means 24 kilobyte. Yeah, I mean, if you are like a software engineer, conventional software engineer, Java engineer, Rust engineer, you may laugh at this, say, okay, 24 kilobyte is nothing. But yeah, in the EVM ecosystem, if you write a smart contract that exceeds, that's actually is totally useless. And it also makes issues, in expanding your project. When you have a big team, I don't know, a project with multiple, developers, and people work on different things, and they need, to use a smart contract or to enrich a smart contract. That's also become kind of issues, because that may intervene in your area. So I try to show you this issue with one example so you can actually see how it works. First, you can see how you can firstly analyze and find the size of a smart contract in your development ecosystem. So for this video, I use Truffle, but you can use the same tool for Hardhat and other ecosystems as well. So first we walk through that. And after that, I will show you a way how to optimize, a smart contract, a larger scale smart contract, and cut it to half. I mean, of course, there is no any magic formula here. You've got to analyze the code. You need to understand the code, and you need to figure out a way to optimize the code size in a way to not basically mess around with the logic of the code, because you want to retain same logic without changing the logic, but you want to optimize the code. So that requires a lot of heuristic, a lot of analysis here. So I try to make this video as short as possible, and let's do it. All right, folks, so this is our code here. So here is one example code, and over here you can see this project comprises multiple, smart contracts. And so it's a typical, larger scale industrial commercial blockchain app. And first thing we are going to do is basically running, our analyzers in order to see the size of each smart contract. So here, when we talk about size, it's not in terms of number of characters inside of the code or the string size. It's about, for example, instantiations and the structures you basically use in your code, in your smart contracts, and how its runtime code, how the size of runtime code would be, inside of the EVM. So there are number of different tools, like I said before, but one of the very practical, useful plugins for Truffle and as well as actually Hardhat and other ecosystem is contract size. So the first thing you need to do, you need to install this tool. So it's called npm install Truffle contract size, and you can install this one. And it takes a while to install that, so I try to skip this part here. All right, after the installation, then like I said, you can use this plugin for Truffle, but also you can use the alternative, same tool basically for Hardhat and other ecosystem. So but here our basically showcase is our showcase environment is in Truffle. So we use Truffle run, and also here we run the tool. It's called contract size. So let's see what we get. So as you can see here is the name of contract, and here is associated size, basically the size of that contract. So if you scroll down here, many contracts are just very small, teeny tiny contract, but here we can see a very large contract. So we have default factory, which is relatively big, and this contract actually is my optimization on this project. And as you can see, I cut this almost to like half, or like 40% smaller, which is okay. So like I said before, if you exceed like 24 kilobyte, then you can't actually compile and deploy your code on the chain, especially for the EVM. For other ecosystems, we have different set of limitations. So what is our basically goal here? Our goal is to figure out what caused this contract to be that much big, and what we can do in order to basically optimize its size. Okay, so there is no any magic formula here. There are a lot of heuristic. First, we need to understand the code. Then we need to understand the logic. In terms of logic, and then when we understand the logic, then we need to do our best in order to make the code better. So yeah, we have a whole bunch of other contracts. So I skip them and I focus on default factory. What we are going to do first is to basically take a look at the code and see what is the potential issue with that, how we can basically preserve the same core logic but optimize the code. Yeah, so there are a lot of heuristic, but the principle is the same. The approach is the same, but of course you can apply that to any contract, but of course it depends on the code and logic of the contract. So we try to understand the logic, we try to understand and take some steps, certain steps, to analyze that. So here is the default factory contract, and of course it's expected to generate basically multiple instantiation of different contracts. So as you can see here, we have several imports, and this is very common problem. I've been working on many industrial projects, and I see many contracts that follow the same template and so on, and many times we have like a lot of redundancy in using libraries and other contracts in our code. It's a very common issue. It's not just for blockchain, it's also for other ecosystem, any industrial ecosystem, So this is something that we need to, of course, take care of that first and foremost, and see, is there any duplication? Do we need all of these libraries or all of these smart contracts necessarily to be here? Do we need all of these local states and the functions here? So that's one thing, and of course that would be sometimes time consuming and complex process. And then if we scroll down here the code, we can see default contract. We have create privilege manager, or it's like something like permission management. So it's also common in blockchain ecosystem. In larger scale project, we have different privileges, admins, users, etc. And of course we do have this. We have new instance here. Then we have create tenant. Tenant is a upgradable contract, and we basically instantiate that as well here. Then we have code contract is like a logic of this upgradable contract. So we have a check, and then basically instantiate this contract as well. And then we have generic Dapps controller. Again, we have instantiations here. and so on and so forth. So as you can see here, the size of a string code, I mean the number of characters and string is not 24 kilobyte or 23 kilobyte, but the instantiation actually is one of the main reasons, and of course the libraries here. So what we can do here, I think the combination of that, we can of course cut off some of these. We can also perform analysis on any of these sub libraries, based on the info we got here, to see about the size and how useful is that, where we need to focus. For example, here if we have like, I don't know, generic Dapps controller types library, if we go here, we can see something about that. For example, we can see, okay, the size here is like very small. So probably if we optimize that, it doesn't really impact, here that much, So of course it would be helpful, but not that many. But inside of these libraries, there might be also other libraries, So here we have some big ones like delivery manager. We do have some basically larger scale contracts. So we got to, for example, we can narrow down. Way is to basically, instead of having multiple instantiation, we can actually make a constructor and do it once, and therefore we can get rid of that and provide, potentially we can resize the code. So we can test the idea and see what happened after the modification and what we can gain here. Alright guys, so here, in order to make the video actually shorter, I performed the optimization, and here is the result. So I call this default factory, let's say optimized, and I'm trying to explain you what I've done here. So as you can see in the non-optimized code here, whenever we basically invoke this function create tenant, we make a new instance of this code, right? This basically contract. And that can add up basically to the size of the contract and to the byte code. So here, actually, I made a constructor, and I basically, because here, as you can see, I put a constructor, and once basically we deploy the contract, we create one instance of tenant here, so that we don't need to each time make a new instance of that. And that alone actually can save a lot of space for us, and it doesn't actually mess with its logic at all, based on this project, this contract. Right, so as you can see here, we basically optimized up to 40%, 45%, and we reduced the size from 23.15 kilobyte to 14.32 kilobyte. And now it's ready for further, expansion, for further development, and we have actually way more faster code, more optimized code. So yeah, that was it, guys. So as you got the lesson here, you need to basically analyze the code, and especially looking for instantiations, and also unused local states, unused libraries and imports, and look into them, in a nested way, and figure out how you can actually optimize the code without changing the logic, and I mean, sometimes the logic might be problematic, but that has a different story. But in general, your optimization code, I mean, as a general principle, should not actually change anything in the logic. The core logic should remain the same, especially when the project is already established, and the algorithm and everything's are okay. All right, guys, so that was it. I hope you enjoyed this video and you find it informative and useful for your career or for your whatever you are doing. For example, for a blockchain ecosystem, if you are performing code audit or optimization, or you are a developer. So if you find this video useful, please don't forget to subscribe, to follow me on YouTube and elsewhere other social media. The links that you can find in the description below. And don't forget also to, if you like, you can also support me via Patreon and other links for donations like crypto. That would be very motivational, and encourage me to make more unique, specific videos for you and make them as simple as possible for everyone to understand this. I am a blockchain engineer and also security auditor, and cybersecurity researcher. So that's it, and I hope to see you soon, in the next video. And cheers.